Alright, we're off and running with Blood Gas of the Week case number 3. We're going to jump straight to interpretation, so if you need a refresher on normal values or how to interpret blood gases, go check out the how-to videos, and if you haven't already, look at the case scenario above, write down your blood gas analysis, and then play out the video. Alright, let's go. An 11-year-old male castrated golden retriever is presented following an episode of collapse on a walk. The owners report a several-day history of waxing and waning appetite and lethargy. This morning on the walk he seemed tired, and then suddenly he groaned, collapsed, and he seemed to be unconscious for about a minute. On the way to the hospital, he's conscious but weak and breathing heavily. On arrival, he's non-ambulatory, laterally recumbent, and panting heavily. Mucous membranes are pale with a prolonged capillary refill, the heart's difficult to hear, pulses are weak with pulse deficits, and he has an abdominal fluid wave. IV access is immediately obtained, blood collected for analysis, and he's connected to the monitoring gear. The ECG shows electrical alternans, and the fast ultrasound shows pericardial and abdominal effusion. About this time, the blood gas comes back, and here's what we've got. So, step number 1, as always, is to see if we have an arterial or a venous sample. This one's venous, so that means we're going to move straight on into our acid-base analysis. The first step is to evaluate the pH, which is high at 7.48, so this is an alkalemia. Alkalemia can be caused by either a low PCO2 or a high bicarbonate. Our patient has a low bicarb, so that's not the problem. His problem is a low PCO2, which means that his problem is a respiratory alkalosis. We would expect to see a metabolic acidosis as compensation, which is low bicarbonate, and that is what we've got. If you prefer the tic-tac-toe method, we see the pH is high, which is an alkalemia. The CO2 is low, which means we have a respiratory alkalosis, and the bicarbonate is low, which means there's a metabolic acidosis. Now we see which process lines up with the pH. In this case, it's the CO2, so the respiratory component is causing the primary disturbance. Our patient has a respiratory alkalosis. The bicarb's moving in the opposite direction, a metabolic acidosis, so this is compensation. If you want to be certain that that's really what's happening, then we're going to move on to the next step and calculate the expected compensation. Since some of our really sick patients can have more than one problem that can cause changes in the blood gas, we use these mathematical formulas to determine if the changes that look like compensation really are compensation, or if they're not, then we need to go looking for a secondary problem. When the primary problem is an acute respiratory alkalosis, the problem says for every 1 point decrease in the CO2 below normal, the bicarb should decrease by 1/4 of a point. So let's look at our patient. Step 1 is to see how much the CO2 has changed from normal. So normal CO2 is about 40, and our patient's CO2 is 26. 26 from 40 is 14. Next, we're going to see how much the bicarb should decrease. So 14 times 0.25 is about 3.5. And then we're going to take that 3.5 and subtract it from 20, because 20 is the midpoint of the normal bicarbonate range. So 20 minus 3.5 is about 16.5, is 16.5. We need to put a range on there because not every patient has a normal bicarb of 20 and not every patient has a normal CO2 of 40. So we're going to account for that, in this case, with a range of about 2 on either side. So 16.5 minus 2 is 14.5. 16.5 plus 2 is 18.5. And we're going to look and see our patient's bicarbonate is 17. It does fall nicely into that range. So our patient has a compensated respiratory alkalosis. Thanks very much for watching. If you're finding these videos helpful, please like and share them on Facebook and Twitter. It'll help get the webpage to start showing up in Google searches. Until next week, keep the rubber on the road and the blood inside.